Welcome to the new lecture. In this lecture, we will introduce free space optical communication systems and we will introduce the concept of mixed RF FSO cooperative relaying systems. In order to understand these topics, I also refer you to my previous lectures, lecture 11 and 12, in which I have already introduced what is cooperative fixed gain AF relaying system and the variable gain AF relaying system, because the cooperative relaying system has been introduced in these two lectures. So free space optical communication is motivated by the major spectrum licensing and scarcity in radio frequency RF systems. The EM waves are basically which are sub 6 gigahertz or those which are even into millimeter waves are basically suffering from scarcity. The range of carrier waves, the carrier frequencies that are available are very less, and therefore various solutions are being envisaged. One of those solution is to signal in optical domain. It has been traditionally done in optical fiber communication systems, but there is a latest technology that is being proposed in 6G communications, which is termed as free space optical communication systems. Free space optical communication system basically can be compared with the previous things like radio frequency. So spectrum is a scarce, spectrum is regulated. You need a lot of money to buy and purchase the spectrum. Multipath fading is there, susceptible to eavesdropping, and large components are required. While in case of fiber optics, although we go in optical domain and there is large bandwidth that is available, but it requires a cumbersome digging and trenching process and time consuming process for installing these fiber optic cables beneath the earth. While free space optical communication is just transmitting the signal through light or in infrared wavelength, and there is a huge bandwidth. Licensing problem is not there because it has not been used that much. It is easy and quick to install, so deployment is very easy. Small light components are there which are available in market, and it is a line of sight communication, so it is very secured compared to RF systems. So basically, optical wireless communication systems are categorized in three categories. So there is FSO, in which the wavelength lies between 700 nanometer to 1 millimeter. Visible light communication, VLC, that is between 390 to 700 nanometers. And ultraviolet communication, which lies between 200 to 280 nanometers. So we in this lecture are focusing on FSO systems. What are the various applications? Uh, for backhauling in cellular networks, I have a separate slide for backhauling purposes. Communication with unmanned aerial vehicles, satellite to satellite links, laser communication for naval applications, satellite to submarine communication, disaster recovery. So you can see that a FSO transmitter and FSO receiver wirelessly can send optical signals on a wireless channel, and it is of immense benefit to researchers. The mode of propagation is basically in this terahertz domain near infrared. So this is the wavelength of operation for FSO systems, which comes under the broader category of optical wireless communication systems. How they can be used as backhaul networks. So backhauling requires a very large amount of data transmission. So a very high data rate at low latency is required for 5G communication systems. Traditionally, T1 and E1 lines were used, then optical fibers were used, but we have already seen that these processes are cumbersome. So when the wired links cannot be deployed, RF and FSO solutions can be there. So basically, FSO is for line of sight uh, communication. So if a line of sight can be maintained between the transmitter and receiver, it is possible to send very high data rates. And practical 5G or 6G implementations will require combination of both non-line of sight and line of sight connections. And that's the focus of cooperative relaying, in which one link is RF and other link is FSO. But FSO links suffer from a lot of challenges. You can understand we are transmitting at a very small wavelength, which means very large frequency. The signal suffers attenuation obstructions. There is effect of weather conditions like sunlight and rain. Apart from that, the basic thing is the alignment between the transmitter and the receiver, and something which is called scintillation. Scintillation is atmospheric turbulence. I will define that in a meanwhile. So when we want to analyze FSO channel, we need first of all to model the path loss. The path loss is basically distance dependent loss. So it is exponential decay in the signal as it travels. Then there is atmospheric turbulence, which is also called scintillation, which is caused by temperature variations in the atmosphere. So if the temperature changes, the refractive indices of the medium and atmosphere changes. Due to that, N1 and N2 changes, the refractive indices changes, the signal suffers degradation in optical domain in FSO transmissions. And this is of major concern, and in modeling is required for that. There is another con- context of pointing errors. We know that FSO communication system is a line of sight communication, and therefore the transmitter and receiver must see each other. For that, the pointing error becomes very important, because whenever there is slightest of transmitter or receiver sway due to thermal expansion or due to earthquakes or by any means, then the misalignment between transmitter and receiver will lead to pointing errors. I am always including the references in this slide, so you can refer to these papers if you want detailed description of these things. How do we model atmospheric turbulence? So first of all, if it is weak, it can be modeled using log normal distribution, strong using negative exponential, moderate to strong gamma gamma model. But there are few models which are coming like double B-pole distribution, double generalized gamma distribution, alpha mu distribution, Malaga distribution. These are slightly more accurate, and they can be used to model the atmospheric turbulence from a regime of weak to moderate to strong, and therefore they are of prime importance. What are the mitigation techniques that have been proposed in literature? Like if FSO has these problems, how to overcome these problems? Aperture averaging has been introduced. You increase the size of the radius of the receiver, which is going to absorb the optical signal. It can only serve you some extent only. You can change the modulation encoding, which means like you change the order of modulation. So if the channel is favorable, the conditions are good for transmission, you use higher order modulation scheme like 64 QPSK. But when the channel condition deteriorate, in FSO communication, you lower the order of the communication system. So you use less number of bits per modulated symbol, right? That is changing the modulation scheme. Diversity techniques, like you use multiple lasers and multiple photodiodes. You can understand that lasers are basically transmitters and photodiodes are receivers. And the latest one which has come is simultaneously using RF and FSO communication system. So I have a separate slide on that. That is where we are focusing in this lecture also. These come under the broader category of cooperative relay systems that I already introduced in lecture number 11 and analyzed mathematically in 11 and 12. You can see those lectures. So there is a concept of mixed RF FSO system which was proposed in the 12th reference by Lee. And for amplifying forward trading, they introduced it. And it was like we use uh, RF for one hope and FSO for another hope. There, then there were multiple things like effect of interference was evaluated, multi-user diversity for RF FSO in reference number 15 was studied, and new fading channels like double generalized gamma channels were studied in reference number 16. So what are these cooperative relaying systems? Cooperative relaying systems, I just repeat again, is that there is a source node, a relay node, and a destination node. We assume that the source node directly cannot communicate with the destination node. So there are two hopes of communication. First is the SR link, and the second one is the RD link. In SR link, we send the signal to relay. The relay receives the signal. It can either amplify and forward it, which is less efficient, but it is very simple, or it can decode the signal, encode it, and then send. That comes under the broader category of decode and forward link, which is complex but has a better performance. Now, in mixed RF FSO communication system, you basically what you do, you use one hop as RF and other as FSO, depending on whether it is downlink or uplink. What is that? That system has a major advantage that now source node communicates with the destination node through a relay node, and source to relay is suppose RF, and the relay to destination link is FSO link. In this form of communication, you have best of both worlds. Like RF is low frequency. If there is the frequency is low, you can understand that the losses, the free space particle path loss as per Friis formula is very less, and therefore it is robust to fading. It is low cost implementation. The connectivity during mobility is there because you do not require line of sight communication. You require non-line of sight communication. And these all conditions favor that RF communication, which is existing infrastructure, so you can use that. But you want more bandwidth also. So if you want more bandwidth, you can go for FSO communication systems also. Because now in this hole, what you can do, you can have a very high bandwidth. There is an inherent security because it is a line of sight communication system. Transmitter and receiver always view each other, and therefore you can understand that the pointing error is minimized. Eavesdropping is not possible. You cannot overhear the information. There are no licensing issues because we are operating in such a high frequency range. It has been not licensed at this point. In future, maybe, and it can be readily deployed, which means that you just need one transmitter, one receiver, this transmitter aperture, receiver aperture, FSO link, and that's it. Your communication system is established. So in ad hoc environments, if you are conducting a seminar where you want multiple RF users, what you can do, you can transmit multiple RF signals at smaller bandwidths, and all of them can be multiplexed by the relay node and then sent over a very large FSO communication system. Vice versa is also possible. Like this end can become source and this can become destination, where this will act as a backhaul because you have a very large band. So it is very important to understand that these FSO communication systems are operating a very high frequency and can transmit data rates in gigabits per second. It is in research right now, but yes, they are very much into the business when it comes to the future wireless communication systems. I hope that this video lecture has helped you to understand what is free space optical communication systems and how they can be used in a cooperative relaying structure where it's dual hop system. The first hop is RF, the second hop is FSO. In next lecture, I will derive the SINR of an interference limited amplifier forward cooperative relaying mixed RF FSO systems. So do watch that lecture, and thank you. Thank you.